Hello Year 12, in this video I'm going to go through section 6.4 which is about trigonometric identities. So let's think about the trigonometric identities that we already know. Now the last time I saw you we looked at the reciprocal trig functions. So I've got sec x which is 1 over cos x. We had cosec x which was 1 over sine x. And we had cot x, which is 1 over tan x. Now, of course, we've still got the trig functions that we know and love from the past. We've got tan x, which is sine x over cos x. And we were talking about, because cot x is the reciprocal of tan x, then it's entirely possible to write cot x as cos x over sine x. And then, of course, we've got, finally, sine squared x add cos squared x, which is equal to 1. Now, we proved why that was the case using a unit circle. If you want to go back to your Year 1 book and have a look in, I think it was chapter 10, somewhere like that. Anyway, we did prove that was true. Now we're going to prove something else following from that fact. So we're going to keep sine squared x as add cos squared x equals 1 as being something that we know to be true because we can prove it. Now what I'm going to do with that is I'm going to divide through by cos squared x. If I divide every single term by cos squared x, I get sine squared x over cos squared x. Add cos squared x over cos squared x is equal to 1 over cos squared x. Now by doing that, I'm going to create another identity that's going to be really useful to us. Now sine squared x over cos squared x is the same as tan squared x. Actually, this is so important, I'm going to write it in red. So I've got tan squared x. Cos squared x over cos squared x is just 1. And 1 over cos squared x is sec squared x, which gives me a brand new identity. I'm going to highlight that in a blue colour because we're going to be using that identity today. The thing is, we didn't just have to divide through by cos squared x. We could have divided through by sine squared x if we'd have chosen to. So let's see what happens if we did that instead. So I'm going to start off with my identity that I know and love. Sine squared x add cos squared x is equal to, or equivalent to, 1. And this time I'm going to divide by sine squared x. Now this is a little method to prove these identities that we're deriving today. So I'm going to write down sine squared x over sine squared x. Add cos squared x over sine squared x is equal to 1 over sine squared x. Now in red, if we do that, sine squared x over sine squared x is just 1. Cos squared x over sine squared x is cot squared x. And 1 over sine squared x is cosec squared x, which gives me another identity that I need to learn. Or at least, if you can't learn it because you can't remember it, we can always go back to sine squared x, add cos squared x equals 1, and divide through by sine squared x, or divide through by cos squared x. And I'm going to let you into a little secret. I find those two really hard to remember. So if I forget, I always go back to sine squared x plus cos squared x is 1, and I divide through, and then I know that I'm right. Okay. So why do we need to use those identities? Well, they can be very useful in solving trig equations, and they can also be useful in proving certain facts or identities. Now, example 1 says prove that cosec to the power of 4x, subtract cot to the power of 4x, is the same as, equals, or identical to 1 add cos squared x over 1 subtract cos squared x. What I would like you to do is I'll give you a little bit of thinking time. I'd like you to think how on earth you could make use of either of those identities that we've just learnt to prove that the left-hand side must be the same as the right-hand side. You can press pause while you have some thinking time. And I'm going to go over it now. If I have a look at the left-hand side, I notice something about that. I notice that it's the difference of two squares. And if you've been going round the houses, and if you've been trying to substitute things into cosec squared, cosec to the power of 4x, etc., and you're not getting anywhere, maybe you didn't realise that the left-hand side was actually the difference of two squares. So I'm going to rewrite my left-hand side as cosec squared x add cot squared x multiplied by cosec squared x subtract cot squared x. Now, by doing that, it doesn't look simpler. In fact, it looks more complicated. But there's something that we should be able to do. If I have a look in the second bracket, I can see that I've got a cosec squared x. And in my identity for cosec squared x, I can see that's the same as 1 add cot squared x. What I'm going to do is I'm going to substitute that into here. So I've got 1 add cot squared x, and I'm going to substitute that into my second bracket only. And if I do that, I've got my first bracket multiplied by 1 add cot squared x subtract cot squared x. And you'll notice that that second bracket cancels out to 1. And I'm going to write that to make that very clear that that's what happens. Well, that makes everything a lot easier to handle. So one little trick is to sometimes use the difference of two squares. Proofs can be really tricky with these identities. You need lots and lots of practice. But now I've got to this stage, I can think to myself, right, okay, cosec squared x is the same as 1 over sine squared x. And cot squared x is the same as cos squared x over sine squared x. Notice how my denominators of those two fractions are the same. So now I'm going to add those two fractions together to get 1 add cos squared x over sine squared x. Now, if I think back to what the question was, the right-hand side that I'm trying to get to was 1 add cos squared x over 1 subtract cos squared x. Now, since I know that cos squared x add sine squared x is equal to 1, I therefore know that sine squared x can be written as 1 minus cos squared x. That implies, therefore, that the left-hand side can now be written as 1 add cos squared x over 1 minus cos squared x, which is exactly the same as the right-hand side. I've proved it. QED, boom. I'm very happy about that. And then you get that great feeling that's associated with that buzz of being able to prove something's true. Okay, so I think I've got another one for you to have a go at. Let's go to example 2. I didn't write this one down, so I'm going to find out what my example 2 is. So I would like you to prove that sec squared theta minus cos squared theta is the same as sine squared theta multiplied by 1 add sec squared theta. And what I always start by doing is I always start by just writing down my identities to the right, so I don't forget what I've actually got on my disposal. And I've got cot squared theta add 1 is cosec squared theta. Okay, so I'm just going to put that in a little bubble. Now, I'd like you to have a go. Press pause. Do not look in your textbook, please. I want you to have a go. I want you to see where you can go from here to prove it. And when you give up, please carry on watching. Or even if you succeeded, carry on watching to see if I did the same thing as you. There are lots and lots of routes that you could go down. Some work well, some lead to dead ends. Okay, so I'm going to show you what I would do. Now, I wonder how many of you looked at the left-hand side and thought, oh, look, that's completing the square. If you did that, this is what would happen. You'd end up getting sec theta subtract cos theta multiplied by sec theta add cos theta. And then you'd end up getting to a situation without any squareds in, which means that you can't possibly use the identities that we've just learnt. And I notice that the right-hand side has got squareds in. So actually, it's taking you further away from where you need to be. So I would say that's probably not the best route. And there must be a better one. So if you think to yourself, I'm not really sure about this, why don't you try working with the other side instead? Now with the right-hand side, there's only one thing I can really do, and that's multiply out the brackets. So if I were to do so, I've got sine squared theta plus sine squared theta, sec squared theta. Now I notice that sec squared theta has an identity associated with it. So I think that that's a good route to go down because I've still got squareds in there. So I'm going to rewrite the right-hand side as sine squared theta add sine squared theta multiplied by tan squared theta add 1. So let's see what happens when I do that. I'm going to have sine squared theta add sine squared theta tan squared theta add 1. I've done something wrong here. I'm going to have to pause it. Okay, I just paused my video because I suddenly thought, where on earth is this taking me? You might have gone through this route and got to the same stage as me and thought, oh my goodness, this is looking quite long. It's perfectly possible to go down this route and get an answer, but I'm feeling that there's something else that I could have done. When I start to get a feeling of, I'm not really sure if this is going right, I stop. I stop and think to myself, is there an easier way? So actually, it's been quite useful for you to see this process. I'm going to stop and I'm going to go back to the first sentence of my right-hand side. Now I highlighted sec squared theta because I knew that I could substitute tan squared theta add 1, and I knew that that would give me an expression that was identical. But what I started to realise as I was working is it was taking me further from where I felt that I needed to be going. So I'm going to carry on, and instead of making that substitution of that identity, I'm going to replace sec squared theta with 1 over cos squared theta. So I haven't used any of my identities, my new identities yet. Now, I've got to this stage, so I think a much easier thing would now be to do is write sine theta add sine squared theta over cos squared theta. And I'm just going to remind myself what the left-hand side was, because I mustn't forget what I'm trying to do. Now my left-hand side was sec squared theta minus cos squared theta. And if I think to myself, sec squared theta is the same as 1 over cos squared theta. So actually, what I'd really like to do is get everything in terms of cos squared theta. So that's what I need to keep in my head. So what I'm going to do now is I'm going to add these two fractions together. So I've got sine squared theta over 1. But I've just suddenly noticed that sine squared theta over cos squared theta is tan squared theta. And now that's really, really helpful. Because what I'm realising is that tan squared theta is in one of my identities. Now tan squared theta add 1 is the same as sec squared theta. Okay, so that means that tan squared theta must be the same as sec squared theta, subtract 1. I also know that sine squared theta is the same as 1 minus cos squared theta. So by making a substitution for tan squared theta as sec squared theta minus 1 and sine squared theta for 1 minus cos squared theta, I'm noticing now that I can write the right-hand side in the way that I actually want to. So I've got 1 minus cos squared theta, add, so that's sine squared theta, add sec squared theta minus 1. And if I simplify that expression, I've got sec squared theta minus cos squared theta. I do believe that was the same as the right-hand side. I have now shown that that is true. If you want practice with some more identities, you're going to get those in the exercise that accompanies this, which I'll put on Show My Homework. Right, okay, so let's have a look at solving some equations using these identities, which is your next skill that we've got to work on. So I've got an equation for you. Looks like it's in degrees there. So can you try and solve this equation without my help by pressing pause? Okay, right, so I'm going to go through this. Now, we can't solve trig equations if they have two different trig functions in. So I'm noticing that we've got cot theta in the equation and we've got cosec squared theta. Now I know that cosec squared x is the same as 1 add cos squared x in my identity. So I think it would make sense to replace the cosec squared theta with 1 add cot squared theta. So I'm going to highlight that in blue and then I'm going to erase the other one so you can see what I'm doing more easily. So I've got 4 lots of, and replacing the cosec squared theta with 1 add cot squared theta minus 9 is equal to cot theta. Expanding brackets. 4 add 4 cot squared theta minus 9 is cot theta. Simplifying, I can see I've got a quadratic there, so subtract cot theta, and I think that goes to -5 is equal to 0. It looks like I can factorise that, so I'm going to try 4 cot theta, subtract 5, and I think that's going to be cot theta add 1 is equal to 0. I'm just going to multiply that out to see if that works. Yes, it does. That's great. Okay, so therefore I'm going to make my brackets equal to 0. So cot theta is the same as 5 over 4, or cot theta is the same as -1. Now, if I know cot theta is 1 over tan theta, then to find tan theta, that must be the reciprocal of 5 over 4. and therefore tan theta must also equal -1, because the reciprocal of -1, of course, is the same. So I've got two routes that I need to go on to find the solutions of my equation. So I'm going to draw my tan curve. You know how good I am at drawing on here, which is meant to be sarcastic. Now I'm concentrating. And there's my tan graph between 0 and 360. Okay, so it is in degrees. I'm just going to remind myself that by writing 360 degrees there. Okay, so when tan of theta is equal to 4/5, what I want to do is I want to draw a line at y is equal to 4/5, and I notice that I've got two solutions there and there. So my first set of solutions, when tan theta is 4/5, now make sure my calculator's in degrees mode, and my first answer, my shift tan, is 38.7 degrees. So I've got 38.7 down there, and I know that I've just got to add on 180 degrees to that to get my next answer, which is 218.7 degrees. And that's my next answer in red. However, I've got another set of solutions when tan theta is -1. So in blue, I'm going to draw a line at y is equal to -1. And if I shift tan theta, it will probably give me, I'd imagine, a negative answer, which is going to be -45 degrees, which is just there. So if I add on 180 to that, it's going to take me inside the range that I would like it at. There's my solution there. And another 180 degrees takes me to where that hits the curve. So I should see an answer here. So that's going to give me theta is 135 degrees. That makes sense. And if I add on 180 degrees to that, I get 315 degrees, which is there. And if I write my other solution in red on the diagram, I can see that that makes numerical sense. Okay, so I've got four solutions. I'm just going to write them in order. I've got 38.7 degrees, I've got 135 degrees, 218.7 degrees, and 315 degrees. So there were four solutions in that range. Okay, so I have got two test your understanding questions for you to have a go at. Please notice they're in radians. Okay, so please press pause. Okay, I'm going to put the answers up now. I'll make sure that I've got the right answers for the right questions. Right, so for the first one, theta should be pi, or 2 pi over 3, or 4 pi over 3. And for the second one, the correct answers to three significant figures should have been, in order of size, 0.785, 2.55 radians, 3.93, and 5.70. Now, if you got those answers, there's no reason why you can't go straight onto the work that I've set on Show My Homework. But if you didn't get those answers and you'd like to see me go through it, I'm very happy to do so, which I'll do now. Okay, so I'm just going to go through the first one of the test your understanding. Okay, so you were asked to solve 3 sec squared theta, add 3 sec theta is equal to 2 tan squared theta. And that was for values of theta between 0 and 2 pi, actually not including 2 pi, so it's in radians. And I'm just going to write out the fact that 1 add tan squared x is sec squared x, and therefore that tan squared x is going to be sec squared x minus 1, because I've just got a feeling that I might need that. Of course, because I can see a tan squared theta, which I'm going to want to make a substitution with. So I've got 3 sec squared theta add 3 sec theta is 2 lots of sec squared theta minus 1. So just multiplying out is 2 sec squared theta minus 2. And if I make that into a quadratic equaling 0, I should have sec squared theta, add 3 sec theta, add 2 is equal to 0. I think I should be able to factorise that pretty easily. I should pop those brackets there. Right, so I've got, oh yeah, just add 1 and add 2 there. Nice and easy. Okay, so I've got sec theta is negative 2 and sec theta is negative 1. Remember that sec theta is 1 over cos theta, which means it's the reciprocal, so therefore cos theta is going to be negative 1/2, which is the reciprocal of negative 2, or cos theta is going to be negative 1. Now, if you're struggling to solve trig equations because you're just a bit rusty, need more practice, I'll just draw my cos graph out. Great diagrams. You know how good my diagrams are, my perfectly symmetrical cos graphs. I do apologise, absolutely terrible. Anyway, I do know that negative 1 is down here, and of course what I really want to do is just pop some values to pi, quite like pi over 2, and 3 pi over 2. Okay, so when y is negative 1, of course I know that x is pi. So I can write theta is pi. Now if I'm having a look at cos theta is negative 1/2, of course I'd like to look for negative 1/2 somewhere down here. So negative 1/2 is there. Now if I do shift cos theta at negative 1/2, it's actually just going to give me the first answer there, which is 2 pi over 3, which is quite nice. So I'm going to write down the fact that theta is 2 pi over 3. And remember that that's a distance from 0 adding 2 pi over 3. So because of the nature of my cosine curve, I just want to jump back from 2 pi to get that other answer there. So my other answer is 2 pi subtract 2 pi over 3, which is actually 4 pi over 3. So finally my answers are theta is pi, 2 pi over 3, and 4 pi over 3. And 4 pi over 3, if I want to write that on my diagram, is just there. Okay. I'm going to go over the second one, just in case you struggled with that. So to test your understanding, number 2, let's see what the question was. So it wanted you to solve 2 cosec squared x, add cot x, equals 5, up to 2 pi radians. And it wanted it to 3 sig figs as well. Okay, so I think the most important identity I'm going to need here is 1 add cot squared x is cosec squared x. And I can see that I've got a cot x in the equation, so I'd really like to replace the cosec squared x with my 1 add cot squared x there. So I've got 2 lots of 1 add cot squared x, add cot x is equal to 5. So 2 add 2 cot squared x, add cot x is equal to 5. So therefore 2 cot squared x, add cot x, negative 3 is equal to 0. Now to factorise 2 cot x and cot x, so I think I'm going to need to make that a negative 1 in there and a positive 3. Let's just check. 2 cot squared x. Yeah, that works. Lovely. So therefore, cot x is negative 3 over 2, or cot x is equal to 1. Now, because cot x is the reciprocal of tan x, that implies that tan x is the negative of 2/3 or tan x is just 1. So we're back to our tan curve again, which is nice. Not a particularly nice sketch, as usual. Sketches are so helpful, though, even if they're really bad like mine. Okay, so when tan x is negative 2/3, let's focus on that one first. So let's put negative 2/3 somewhere down there. Equals negative 2/3. Right, so when I do shift tan of negative 2/3, it actually gives me the principal solution, which is the first answer closest to 0, which is actually negative 0.588. But that's not in my range, so I'm going to need to go to the next place where that cuts the curve. So I'm going to need to add on pi radians, because remember this repeats every pi radians. And then I'm going to need to add pi radians to that one to get the next solution there. So negative 0.588 add pi radians, it gives me 2.55. And if I add pi to that, I get 5.70. So I can see that x is 2.55 and 5.70. Let's go to the other set of solutions for tan x is equal to 1. That's obviously going to be the positive section there. We know that tan of 45 degrees is equal to 1. So if I just write y equals 1 there, if I were to read down, that's going to be 45 degrees. In radians, that's pi over 4. And if I were to add another pi radians there, that's going to give me 1 1/4 pi radians, which takes me down to 5 pi over 4. So if I turn those into decimals, pi over 4 is 0.785 and 5 pi over 4 is 3.93. So you can write those in order if you want to, but it doesn't really matter. Okay, so go to Show My Homework to have a look at what the task is that I've set you for the exercise. Any problems, please let me know, and I may well post another video going through some proofs if anybody asks me to. Good luck. Thanks very much.